We're now going to use a graph to locate something called the absolute maximum and the absolute minimum. Whereas in local maximum and local minimum, we said within a small interval of values, where is the high or low point? For absolute maximum and absolute minimum, the interval tends to be bigger over some wider range of values. Where is the absolute highest point on the graph, and where is the absolute lowest point on the graph? Sometimes, rather than using the word absolute, we use the word global, as in global maximum or global minimum. So here are the definitions. Let f denote a function defined on some interval I. If there is a number u in that interval I, for which f of x is less than or equal to f of u, in other words, the values of the function are no bigger than f of u, for all x in I, then f of u is referred to as the absolute maximum on the interval I. The way we say that is similar to local. We say the absolute maximum of f is f of u and occurs at x equals u. I'll show you a graph that'll help to illustrate this idea in a second. If there is a number v in the interval I for which f of x is greater than or equal to f of v, in other words, f of v is the smallest possible value of the function on that interval, then f of v is the absolute minimum of f, and we say the absolute minimum is f of v and occurs at x equals v. Okay, so the absolute maximum is the highest value of the function on the interval. The absolute minimum is the smallest possible value on the interval. So here is a graph. We want to find the absolute maximum and the absolute minimum from the graph. You can see that the graph exists from x equals 0 through to x equals 5. On that interval from 0 to 5, what is the absolute maximum? What's the highest value of the function, in other words? Yeah, the absolute maximum is 6, and it occurs at x equals what? At x equals 3. What's the absolute minimum? What's the smallest value of the function? I could be less than 4, say if I was over here at 1 comma, what, like 2.5-ish, right? What's the smallest value on this function? 1. So we would say the absolute minimum is 1, and it occurs at x equals 0. As an aside, if you look at this point right here at 4 comma 4, if I draw a little open interval around 4 comma 4, you can see that 4 is a local minimum that occurs at x equals 4, but it is not an absolute minimum because I can find smaller values of the function than 4 from the graph. Here's a second example. Find absolute maximum and absolute minimum if they exist. First, the absolute maximum, what do you think it is based on the graph that you see? Yep, the absolute maximum is 3, and it occurs where? At x equals 5, because you can see that the point 5 comma 3 is the highest point on the graph. You can't get a higher value. The answer to the absolute minimum is a trick because of the open circle that exists at 3, 1. Because there's an open circle at 3, 1, and if that point was closed, it would be the smallest value on the graph. We say there is no absolute minimum. The idea behind that is, if you said the smallest value is 1.0001, I could say, no, it's 1.0001. In other words, we can keep getting closer and closer to 1 with never actually reaching 1, and because of that, there is no absolute minimum value. So bottom line is, when you have open circles on graphs, you have to be very careful about judging whether there's an absolute maximum or absolute minimum value. Here's another graphic, and what you can see is it's kind of U-shaped with a flat spot at the bottom. We want to find the absolute maximum and the absolute minimum here. Based on the graph, what do you think the absolute maximum is? What do you think it is? 4. And occurs at x equals 5. How about the absolute minimum? Yeah, the absolute minimum is 1. And it occurs for lots of x values. It occurs for all x values between 1 and 2 inclusive. You see that? At the flat spot of the graph. The absolute minimum of 1 that occurs on the interval 1 to 2 inclusive is also a local minimum. You see the difference between a local and an absolute? See, the local is just within some interval of values, it's the high point, whereas with the absolute, over the entire domain of the function, it's the highest point. Here we want to find the absolute maximum and the absolute minimum if they exist. Is there an absolute maximum? No. How do we know that? Yeah, there's an arrow on the end of the graph that suggests that the graph is going to keep increasing. And so you can't identify any local or absolute maximum. So we would say no absolute maximum. Is there an absolute minimum? Yes, what is it?
0.
You have an absolute minimum of 0 that occurs at x equals 0 because of the ordered pair 0, 0. That's the smallest value on the graph of the function. One last graphic. So this is a U-shaped graphic. We got a hole in the graph at 3, 2, which appears to be the low point of the graph. And then to the right we have what's called a vertical asymptote at x equals 5, and the graph gets closer and closer to x equals 5 and keeps rising. Is there an absolute maximum? No. No absolute maximum because over the domain the graph keeps increasing as x gets closer to 5 from the left. Is there an absolute minimum? No, because of the hole in the graph at the point 3, 2, which is the low point on the graph. It's the same idea. I can get closer and closer to 2 while remaining larger than 2 and keep getting smaller and smaller values. So no absolute maximum, no absolute minimum is the bottom line here. One final note, something called the extreme value theorem says that if f is a continuous function, and for our purposes we'll just say the continuous function is a function whose graph could be drawn without lifting your pencil off the paper. If you have to lift up, like you would here, with this U-shaped graph with the hole at 3, 2, you'd have to lift your pencil off the paper to jump over that point, right? So this is not continuous on the domain that it's defined. Whereas this function is continuous, right? Because it starts at 0, 0 and keeps increasing to the right. I never have to lift my pencil off the paper. So if you have a continuous function whose domain is a closed interval, a comma b, then the function f is going to have an absolute maximum and an absolute minimum on that interval. So it's called the extreme value theorem because there are extreme values of the function in over the domain for which it is defined. Here's a classic example of the extreme value theorem from economics. If you graph taxes as a function of the tax rate, the smallest tax rate you could possibly have is 0%. And if you have 0% tax rate, your tax revenue is going to be $0, right? Because you're not charging anyone any taxes. So this was, I can't remember, in the early 1900s is when the federal income tax was devised. Before that, there was no federal income tax. If the tax rate is 100%, the revenue will be 0. Why do you think that is? No one would work. And so the idea here is that in between, and I don't know what the graph actually looks like, but in between is some graph that would describe the tax revenue as a function of the tax rate. And so the trick in tax policy is to figure out the tax rate that maximizes your revenue. So the extreme value theorem says there is going to be at least one tax rate that would maximize tax revenue. We just don't know what it is because we don't necessarily know what this curve looks like. We also know there are two tax rates for which tax revenue is minimized.